Now, in this lecture, we'll find out the radius of a circle using two different methods. In the drawing, we have triangle ABC. This circle is inscribed by triangle ABC. Or triangle ABC blocks this circle. In addition, we know that this angle is angle ABC, this is equals to 60 degrees in its size, and this is angle ACB, this is equals to 75 degrees. And we also know that side BC of this triangle ABC equals to 2 units in its length. Again, our mission is to find out the radius of this circle that is inscribed by this triangle ABC. We'll start with the first method. In the first method, we do a construction. That is to say, from point C, we will draw perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB as D. In the next step, I will copy the right triangle BDC in the new page, and we will analyze this right triangle BDC. So actually, this is the right triangle BDC that I copied from the original drawing. Side BC equals to 2 units in its length according to what is given as the equation. And angle DBC equals to 60 degrees. So in this right triangle DBC, cosine 60 degrees will be equal to dB over BC. So I write it down. Cosine 60 degrees equals to dB over BC. So cosine 60 degrees is 1/2. So 1/2 equals to dB over BC. BC is 2, so we substitute BC by 2. In conclusion, we found out that 1/2 equals to dB over 2. We will multiply this equation by 2. And finally, we get that dB equals to 1. So actually, this line segment dB equals to 1 units in its length. We'll continue to focus on this right triangle BDC. On the right triangle BDC, cosine 60 degrees, sinus 60 degrees equals to DC over BC. Okay, sinus 60 degrees equals to DC over BC. Sinus 60 degrees is square root of 3 over 2. That equals to DC over BC, and BC is 2. So in conclusion, we found out that square root of 3 over 2 equals to DC over 2. Here we multiply this equation by 2, and finally we get that DC equals to the square root of 3 units in its length. So here, this is 97 DC, that equals to the square root of 3 units in its length. So, in the same right triangle DBC, we know that the sum of the angles must be equal to 180 degrees, what it is actually true in any triangle. So, which angles we have in the right triangle DBC? This angle, it is the right angle, it is equal to 90 degrees, plus this angle that is 60 degrees, 90 degrees plus 60 degrees, it is 150 degrees. Plus the missing angle, in total, they must be equal to 180 degrees. Therefore, the missing angle must be equal to 30 degrees in its size. So, it is given as the question that the big angle ACB, this is the big angle ACB, that is equal to 75 degrees in its size. So the big angle ACB that is 75 degrees minus the small angle that is 30 degrees, it will be equal to the missing angle. This is the missing angle. That is actually angle DCB, angle DCA. So the missing angle DCA equals to the big angle that is 75 degrees minus the small angle that is 30 degrees. 75 degrees minus 30 degrees, it is equals to 45 degrees. Okay? Again, the big angle minus the small angle equals to the missing angle DCA. Therefore, the missing angle equals to 45 degrees in its size. In the next step, I will copy the right triangle ADC in a new page, and we will analyze this right triangle, triangle ADC. So actually, this is the right triangle ADC that I copied from the original drawing. We already found out that this equals to the square root of 3 units. And this is the missing angle ACD, that equals to 45 degrees. So in this right triangle ADC, the sum of the angles must be equal to 180 degrees. That is to say, 45 degrees plus 90 degrees, that is 135 degrees, plus the missing angle, in total, they must be equal to 180 degrees, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So 135 degrees plus the missing angle, in total they must be equal to 180 degrees. Therefore, the missing angle must be equal to 45 degrees in its size. So, we found out that the right triangle ADC, it is also an isosceles triangle. Why? Because those triangles are equal to each other. And we have the rule that in front of equal angles in the triangle, there are equal sides. So those two sides that are located in front of those two equal angles must be also equal to each other. That is to say, side AD must be equal to side DC. AD equals to DC. But we know that DC equals to the square root of 3 units. So we can write it that DC equals to the square root of 3 units. And for this equation, AD equals to DC equals to the square root of 3 units, we will derive that AD also equals to the square root of 3 units in its length. Line segment AD equals to the square root of 3 units in its length. We can write down in the original domain that line segment AD equals to the square root of 3 units in its length. We'll continue to focus on the right triangle, triangle ADC. In the right triangle ADC, according to the Pythagoras theorem, here by PT is the information for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of all the squares of the perpendiculars. The hypotenuse in the right triangle this is AC, so AC squared equals to AD squared plus DC squared. So AC squared, that is the square of the hypotenuse, equals to AD squared. AD is equal to 3, therefore AD squared is square root of 3 squared, that is 3, plus DC squared. DC is also square root of 3, therefore DC squared is square root of 3 squared, that is 3. So in total, AC squared equals to 3 plus 3, that is 6. AC squared equals to 6. Here we take a root out of this equation. And finally we get that AC equals to the square root of 6 units in its length. So here side AC of this triangle, triangle ABC, equals to the square root of 6 units in its length. In the next step, I will present to you a new rule, and we will implement the new rule in our drawing. The new rule is actually rule number 15. According to rule number 15, the radius of a circle that is inscribed by a triangle ABC that could be any triangle, the radius R equals to the area of triangle ABC that blocks the circle over S, that is the semi-perimeter of the same triangle, triangle ABC. Repeat again. We have in the drawing triangle ABC, and this circle is inscribed by this triangle, triangle ABC. So according to this rule number 15, the radius of this circle that is inscribed by triangle ABC is equals to, the radius R equals to the area of this triangle, triangle ABC that blocks this circle over S, that is the semi-perimeter of the same triangle, triangle ABC. The semi-perimeter of any triangle equals to the perimeter over 2. The perimeter is the sum of the side lengths of the triangle, that is to say it is AB plus BC plus AC. And if we divide the perimeter by 2, we get the semi-perimeter S. So the radius of this circle R equals to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle, triangle ABC. So we can actually implement rule number 15 in our drawing. Actually, whenever you have a circle that is inscribed by a triangle, you can implement rule number 15, and here we have this circle that is inscribed by triangle ABC, therefore we can implement here rule number 15. So we define the radius of this circle R, so the radius of this circle R will be equal to the area of triangle ABC that blocks this circle over the semi-perimeter of the same triangle, triangle ABC. Repeat again. According to rule number 15, the radius R of this circle is equals to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle, triangle ABC. The area of any triangle is equals to the base of the triangle times the height to the base over 2. And we have to divide the area of the triangle by S. So we'll choose the base of this triangle as AB. So the base is AB times the height to the base. The height to the base must create 90 degrees with the base, and we can see that CD creates 90 degrees with the base, so the height to the base will be CD. The height is CD over 2, all divided by the semi-perimeter of the same triangle, triangle ABC. AB, the base AB is square root of 3 plus 1. Times the height DC is square root of 3. All divided by 2. That is actually the area of triangle ABC. We have to divide the area of triangle ABC by S, that is the semi-perimeter of the same triangle, triangle ABC. The semi-perimeter of any triangle is the perimeter over 2. The perimeter of triangle ABC is AB plus AC plus BC. AB plus AC plus BC. And if we divide the perimeter by 2, we get the semi-perimeter S. This expression is the area of triangle ABC. And the value of this expression, it is actually 2.366 square units. That is to say, the area of this triangle, triangle ABC, it is equals to 2.366 square units divided by the semi-perimeter, that is AB, and AB is equal to 3 plus 1 plus AC. AC is equal to 6 plus BC. It is given us the question that BC equals to 2 units in its length, so it is plus 2, all divided by 2. So actually found out that the radius of this circle, the radius that we are looking for, the radius R equals to 2.366 over this expression. This expression, it is actually the semi-perimeter of this triangle, triangle ABC. The value of this expression is equal in total to 3.591 units. And 2.366 over 3.591, it is equal to 0.6589. So actually found out that the radius R of this circle, that is the radius that we are looking for in this question, the radius R equals to 0.6589 units. And that is the answer to our question. In the next step, I will present to you how to find out the radius of this circle according to the second method. So in the second method, we will define the center of this circle as O. We will define the point of tendency of tangent AC with this circle as F. We will define the point of tendency of tangent AB with this circle as E. And finally, we will define the point of tendency of tangent BC with this circle as D. In the next step, we will join points O and D together by a straight line. Point O is the center of the circle, point D is the point on the circle itself, therefore OD is the radius of this circle. So we define the radius of this circle as R, therefore OD equals to R. We can implement here rule number 1. I'll repeat quickly on rule number 1. According to rule number 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have tangent AB, that is tangent to this circle at point M. Point M is the point of tendency of tangent AB with this circle. And we have also the radius OM that is drawn to point M. That is to say, it is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees. Okay, so we can implement rule number 1 in our drawing. Why? Because in our drawing we have the radius OD that is drawn to point D. That is to say, it is drawn to point D, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius DO, according to rule number 1. If BC is perpendicular to DO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule number 1. We join points O and D together by a straight line. OE is the radius of this circle that is equal to R according to our definition. Again, we have the radius OE that is drawn to point E, that is the point of tendency of tangent AB with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius EO. If AB is perpendicular to EO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to the same rule, rule number 1. We join points O and F together by a straight line. OF is the radius of this circle that is equal to R. Again, the radius OF is drawn to the point of tendency, therefore according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. We can actually implement here rule number 2 also. A bit quickly on rule number 2. According to rule number 2, the lengths of two tangents from a common standpoint to a circle are equal. We have a circle and we have also the common standpoint point P. From the common standpoint point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule number 2, they are equal to each other. That is to say, PA equals to PB. So we can actually implement rule number 2 in our drawing. Why? Because in our drawing, if we focus on the common external point C, from the common external point C, we have two tangents to this circle, tangent CF and tangent CD. And according to rule number 2, they are equal to each other. That is to say, CF equals to CD. So can I now here that CF equals to CD according to rule number 2. Likewise, we'll focus on the common external point B. Here, from the common external point B, we have two tangents to this circle, tangent BE and tangent BD. And according to rule number 2, they are equal to each other. That is to say, BE equals to BD. So can I write it that BE equals to BD according to the same rule, rule number 2. In the next step, we'll join points O and C together by a straight line. And we'll also join points O and B together by a straight line. And we'll prove that the yellow right triangle BOD is congruent to the green right triangle EOB. So I write it down. We'll prove that the yellow right triangle OBD we prove that the yellow right triangle BOD is congruent to the green right triangle BEO. So why those two right triangles congruent to each other? First of all, side EO of the green triangle equals to side OD of the yellow triangle. They are both the radii of the circle, therefore they are equal to each other. So side EO of the green triangle EOB is equals to side OD of the yellow triangle repeat again. Side EO of the green triangle equals to side OD of the yellow triangle. They are both the radii of the circle, therefore they are equal to each other, they are equal to R. is the radius of the circle. In addition, BE equals to BD according to rule number 2. Here, BE equals to BD according to rule number 2. Side BE of the green triangle equals to side BD of the yellow triangle according to rule number 2. Repeat again. Side BE of the green triangle equals to side BO of the yellow triangle according to rule number 2. And finally, side OB is a common side that belongs to both triangles, so we can write down that OB equals to itself as a common side that belongs to both triangles. Repeat again. Side OB equals to itself as a common side that belongs to both triangles. So actually we proved that all the three sides of the green right triangle EOB are correspondingly equal to all the three sides of the yellow triangle BOD. Therefore we proved that the green triangle EOB is congruent to the yellow triangle OBD according to side rule. So I write it down. The yellow triangle OBD, congruent, this is the sign of congruent, to the green triangle BEO according to side rule. And from the fact that those two right triangles can go into each other, we will derive that those two angles are also equal to each other. According to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding angles must be also equal to each other. So in the green triangle we have this angle, it is actually angle EBO. And it is equal to this angle in the yellow triangle, this is actually angle OBD. So if we define one of those two angles as theta, then the other angle must be also equal to theta because they are equal to each other. So theta plus theta equals to 60 degrees according to what is given us the question. That is to say 2 theta equals to 60 degrees. We divide this equation by 2 and finally we get that angle theta equals to 60 degrees over 2, that is 30 degrees. So actually this is angle theta that is equal to 30 degrees in its size. So in the next step I will copy the yellow triangle OBD in a new page and we will analyze this yellow triangle OBD. Side OD equals to R, it is the radius of the circle. So actually, this is the right yellow triangle OBD that I copied from the original drawing. This is angle theta that is equals to 30 degrees in its size. So in this right triangle OBD, tangent 30 degrees equals to OD over BD. Repeat again, in the right triangle OBD, tangent 30 degrees equals to OD over BD. OD equals to R, so it is R over BD. In conclusion, found out that tangent 30 degrees equals to R over BD. Here we multiply this equation by BD, and we get that BD times tangent 30 degrees equals to R. Here we divide this equation by tangent 30 degrees. And we get that BD equals to R over tangent 30 degrees. So this 9 segment BD equals to R over tangent 30 degrees in its length. So I write it down in the original drawing here. This 9 segment BD equals to R over tangent 30 degrees in its length. So we repeat on the same process on those two right triangles. That is to say, we prove that the orange right triangle ODC is congruent to the pink right triangle OFC. So write it down. We'll prove that the orange right triangle ODC is congruent to the pink right triangle OFC. So why those two right triangles congruent to each other? First of all, side OF of the pink triangle equals to side OD of the orange triangle. They're both the radii of the circle, therefore they are equal to each other. OF equals to OD equals to R. In addition, CF equals to CD according to rule number 2. I'll repeat again. Here we already found out that CF equals to CD according to rule number 2. So side CF in the pink triangle equals to side CD in the orange triangle, according to rule number 2. And finally, we have side OC is a common side that belongs to both triangles, so OC equals to itself is a common side that belongs to both triangles. So actually proved that all the three sides of the pink triangle OFC are corresponding equal to all the three sides of the orange triangle ODC. Therefore proved that the pink triangle OFC is congruent to the orange triangle ODC, according to side rule. So the pink triangle OFC is congruent to the orange triangle ODC, according to side rule. And from the fact that those two right triangles can run to each other, we derive that those two angles are also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can run to each other, therefore those two corresponding angles must be also equal to each other. So if one of those two angles is alpha, then the other angle must be also equal to alpha because they are equal to each other. So alpha plus alpha is equals to 75 degrees according to what is given as the equation. That is to say 2 alpha equals to 25 degrees. So 2 alpha equals to 75 degrees, we divide this equation by 2, and finally we get that angle alpha equals to 75 degrees over 2, that is 37.5 degrees. So actually, this is angle alpha, that is equals to 37.5 degrees in its size. In the next step, I will copy the orange triangle ODC in a new page, and we will analyze this orange triangle ODC. Side OD equals to R, it is the radius of the circle. This is angle alpha, that is equals to 37.5 degrees. So actually, this is the orange triangle ODC that I copied from the original drawing. In this triangle ODC, tangents 37.5 degrees equals to OD over DC. Tangents 37.5 degrees equals to OD over DC. OD is R, it is the radius of the circle, over DC. So tangents 37.5 degrees equals to R over DC. Here we multiply this equation by DC, and we'll get that DC times tangents 37.5 degrees equals to R. Here we divide this equation by tangents 37.5 degrees, and finally we get that DC equals to R over tangents 37.5 degrees. So this is side DC, this is equals to R over tangent 37.5 degrees. So I write it down here. This is side DC, this is equals to R over tangent 37.5 degrees in its length. From the drawing, it is very easy to see that side BC equals to BD plus DC. Repeat again. Side BC equals to BD plus DC. According to what is given as the equation, BC equals to 2 units in its length, so we substitute BC by 2, and it is equals to BD. We already found out that BD equals to R over tangent 30 degrees, so we substitute BD by R over tangent 30 degrees. Plus DC. DC equals to R over tangent 37.5 degrees, therefore we substitute DC by R over tangent 37.5 degrees. So in conclusion, we found out that 2 equals to R over tangent 30 degrees plus R over tangent 37.5 degrees. We take R a second factor from out of those two expressions, and we get that 2 equals to R, so R was taken as a second factor. So what is left from this expression after we took R as a second factor? What is left is actually 1 over tangent 30 degrees. And what is left from this expression after we took from it R as a second factor? What is left is actually 1 over tangent 37.5 degrees. So in conclusion, we found out that 2 equals to R times 1 over tangent 30 degrees plus 1 over tangent 37.5 degrees. So 2 equals to R, and 1 over tangent 30 degrees is equals to 1.732 plus 1 over tangent 37.5 degrees. 1 over tangent 37.5 degrees equals to 1.3032. So in conclusion, we found out that 2 equals to R, and 1.732 plus 1.3032 equals in total to 3.0352. Again, in conclusion, we found out that 2 equals to R times 3.0352. Here we will divide this equation by 3.0352, and finally we get that R, the radius that we are looking for, is equals to 2 over 3.0352. 2 over 3.0352 equals to 0.6589 units. So we actually found out that the radius of the circle that we are looking for R, it is equals to 0.6589 units. This is the answer to the question. So actually, in both methods, we found out that the radius R of this circle that is described by this triangle ABC is equals to 0.6589 units. In the next step, I will summarize the lecture. We start with the first method. So, in this lecture, we found out the radius of this circle that is inscribed by this triangle ABC. So, it is given us the question, this is angle ABC, this is equals to 60 degrees in inside, this is angle ACB, this is equals to 75 degrees. In addition, we know that this side BC of triangle ABC equals to 2 units in its length. Again, our mission is to find out the radius of this circle that is inscribed by this triangle ABC. Okay. In the first method, we did a construction that is to say, from point C, we draw perpendicular on side AB. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and side AB as D. In this way, we created the right triangle BDC. So I copied the right triangle BDC in a new page and we analyze this right triangle BDC. This is the right triangle BDC that I copied from the original drawing. Angle BDC equals to 60 degrees and side BC equals to 2 units according to what is given as the question. This angle equals to 90 degrees according to our construction. In the right triangle BDC, cosine 60 degrees equals to BD over BC. So cosine 60 degrees is 1/2. That equals to BD over BC. BC is 2, so we substitute BC by 2. In conclusion, we found out that 1/2 equals to BD over 2. We multiplied this equation by 2 and finally found out that side BD equals to 2 units, side BD equals to 1 unit in its length. So this is side BD is equals to 1 unit in its length. We continue to focus on the right triangle ABD. In the right triangle ABD, sinus 60 degrees equals to DC over BC. Again, sinus 60 degrees equals to DC over BC. Sinus 60 degrees is square root of 3 over 2. That is equals to DC over BC. BC is 2. So in conclusion, we found out that square root of 3 over 2 equals to DC over 2. Here we multiply this equation by 2. And finally, we found out that DC equals to the square root of 3 units in its length. This side DC equals to the square root of 3 units in its length. So I can write down in the original drawing, this is side DC that is equals to square root of 3 units in its length. We continue to focus on the right triangle DBC. In the right triangle DBC, as it is true in any triangle, the sum of the angles is equal to 180 degrees. So which angles we have inside the right triangle DBC? We have this angle that is a right angle that is equal to 90 degrees in its size, plus this angle that is equal to 60 degrees. 90 degrees plus 60 degrees is 150 degrees, plus the missing angle. In total, they must be equal to 180 degrees. So the missing angle must be equal to 30 degrees. So angle DCB equals to 30 degrees in its size. The big angle ACB equals to 75 degrees, according to what is given as the question. So the big angle ACB minus the small angle DCB must be equal to the missing angle ACD. So the big angle minus the small angle equals to the missing angle, that is angle ACD. That is to say, the big angle is 75 degrees minus the small angle, that is 30 degrees, equals to the missing angle ACD. So 75 degrees minus 30 degrees, it is 45 degrees. So the missing angle ACD equals to 45 degrees in its size. So I copied the right angle ACD in a new page, and we analyze this right angle ACD. This is the right angle ACD that I copied from the original drawing. We just right now found out that angle ACD equals to 45 degrees in its size, and we already found out that CD equals to square root of 3 units in its length. In this right angle triangle ADC, the sum of the angles must be equal to 180 degrees. So which angles we have inside the right angle ACD? We have this angle that is 45 degrees, plus this angle is equal to 90 degrees. 90 degrees plus 45 degrees, it is equal to 135 degrees. So 135 degrees plus the missing angle, in total they must be equal to 180 degrees. Therefore the missing angle here must be equal to 45 degrees in its size. So actually found out that those two angles are both equal to 45 degrees, therefore they are equal to each other. And we have the rule that in front of equal angles in the triangle, they are equal size. So those two sides that are located in front of those two equal angles must be equal to each other. That is to say, side AD must be equal to side DC. But we have already found out that DC equals to the square root of 3 units. So you can write here that DC equals to the square root of 3 units. And from this equation, AD equals to DC equals to the square root of 3 units, we will derive that AD equals to the square root of 3 units. Here, AD equals to the square root of 3 units. So you can write down in the original drawing that this line segment AD equals to the square root of 3 units in its length. We continued to focus on the right triangle ADC. Here we implemented the Pythagoras theorem on this right triangle ADC in order to find out the hypotenuse AC. According to the Pythagoras theorem, in the right triangle ADC, AC squared equals to AD squared plus DC squared. Again, AC squared equals to AD squared plus DC squared. So AC squared, that is the square of the hypotenuse, equals to AD squared. AD is square root of 3, therefore AD squared is square root of 3 squared, that is 3, plus DC squared. DC is square root of 3, therefore DC squared is square root of 3 squared, that is 3. So in total, AC squared equals to 3 plus 3, that is 6. AC squared equals to 6. We took a root out of this equation and finally found out that AC equals to the square root of 6 units in its length. The hypotenuse AC equals to the square root of 6 units in its length. Here, side AC of triangle ABC equals to the square root of 6 units in its length. Okay, in the next step, I presented to you a new rule and implemented the new rule in our drawing. The new rule is actually rule number 15. According to rule number 15, the radius of a circle that is inscribed by triangle ABC, that could be any triangle, the radius R equals to the area of triangle ABC that blocks the triangle over S, that is the semi-perimeter of the same triangle ABC. So here we have a circle that is described by this triangle ABC. So the radius R of this circle, according to this rule number 15, will be equal to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle ABC. The semi-perimeter of any triangle is the perimeter over 2. The perimeter is the sum of the side lengths of the triangle, that is to say it is AB plus BC plus AC, and if we divide the perimeter by 2, we get the semi-perimeter S. So in conclusion, the radius of any circle that is blocked by a triangle, that is described by a triangle, the radius R will be equal to the area of the triangle that is blocks the circle or the semi-perimeter of the same triangle. We can implement rule number 15 in our drawing. Why? Whenever we have a circle that is described by a triangle, we can implement rule number 15. We have in our drawing a circle that is described by triangle ABC, therefore we can implement here rule number 15. According to rule number 15, the radius of this circle that is described by triangle ABC, we define the radius of this circle as R. So the radius R will be equal to the area of triangle ABC over the semi-perimeter of the same triangle, triangle ABC, according to rule number 15. I repeat again, according to rule number 15, the radius R, the radius that we are looking for, of our circle equals to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle, triangle ABC. The area of any triangle equals to the base of the triangle times the height to the base over 2. We choose the base of this triangle, triangle ABC as AB, and we choose, and the height therefore it is DC. Why? Because the height must create 90 degrees with the base AB, and indeed DC creates 90 degrees with the base AB. Therefore the height is DC. So the area of triangle ABC equals to the base AB times the height to the base, that is DC, over 2. Divided by S, that is the semi-perimeter of the same triangle, triangle ABC. We have already found out that the base AB in total equals to the square root of 3 plus 1. AB equals to the square root of 3 plus 1. The height DC equals to the square root of 3. DC equals to the square root of 3, all divided by 2. So this expression in total equals to the area of triangle ABC divided by S, that is the semi-perimeter of the same triangle, triangle ABC. The semi-perimeter of triangle ABC equals to the perimeter over 2. The perimeter of this triangle ABC, it is AB plus AC plus BC, and if we divide the perimeter by 2, we get the semi-perimeter S. So in total, the semi-perimeter of our triangle, triangle ABC equals to the perimeter that is AB plus AC plus BC. And if we divide the perimeter by 2, we get the semi-perimeter S. In total, the value of this expression, that is actually the area of triangle ABC, is equals to 2.366 square units. This is the area of triangle ABC. And the semi-perimeter of the same triangle, triangle ABC equals to AB, that is square root of 3 plus 1, plus AC, that is square root of 6, plus BC, that is equals to 2 units, according to what is given as the equation, divided by 2. In total, the value of this expression, that is actually the semi-perimeter of the same triangle, triangle ABC, the value of this expression in total, it is equal to 3.591. So in total, the radius R of this circle, the radius that we are looking for, R, equals to 2.366 over 3.591, that is actually 0.6589 units. So the radius R of this circle equals to 0.6589 units. We finished with the first method. In the next step, actually presented to you how to find out the radius of this circle that is described by triangle ABC according to the second method. In the second method, we defined the center of this circle as O. We define the point of tendency of tangent AB with this circle as C. We define the point of tendency of tangent AC with this circle as F. And finally, we define the point of tendency of tangent BC with this circle as D. Then we join points O and D together by a straight line. Point O is the center of the circle. Point D is the point of the circle itself. Therefore, OD is the radius of this circle that we defined as R. We have the radius OD that is drawn to point D. That is to say, it is drawn to point D, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius DO. If BC is perpendicular to DO, it means that this angle equals to 90 degrees, and this angle equals to 90 degrees according to rule number 1. We join points O and D together by a straight line. O is the radius of the circle that is equal to R. We have the radius OE that is drawn to the point of tendency. Therefore, according to rule number 1, this angle equals to 90 degrees and this angle equals to 90 degrees. Likewise, we join points O and F together by a straight line. OF is the radius of this circle that is equal to R. The radius OF is drawn to the point of tendency. Therefore, this angle equals to 90 degrees. and this angle also equals to 90 degrees according to the same rule number 1. Then we implemented in this drawing also rule number 2. If we focus on the camera standpoint point C, from the camera standpoint point C, we have two tangents to this circle, tangent CF and tangent CD. And according to rule number 2, they are equal to each other. That is to say, CF equals to CD. Here, CF equals to CD according to rule number 2. Likewise, we focus on the camera standpoint point B. From the camera standpoint point B, we have two tangents to this circle, tangent BD and tangent BE. And according to rule number 2, they are equal to each other. That is to say, BE equals to BD according to rule number 2. Then we join points O and C together by a straight line, and we join points O and B together by a straight line. In the next step, we proved that the yellow triangle is congruent to the green triangle. Why those two triangles can go into each other? First of all, OD equals to OE, they are both the radii of the circle, therefore they are equal to each other. In addition, BD equals to BE according to rule number 2. Here, BD equals to BE according to rule number 2. And finally, side OB is a common side that belongs to both triangles, so we can write down that OB equals to itself as a common side that belongs to both triangles. So we actually proved that all the three sides of the right yellow triangle OBD are corresponding equal to all the three sides of the right green triangle OBE. Therefore, those two right triangles can go into each other according to side rule. And from the fact that those two right triangles can go into each other, we derive that those two angles must be also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding angles must be also equal to each other. So if this angle is theta, then the other angle must be also equal to theta because they are equal to each other. So theta plus theta equals to 60 degrees according to what is given as the question. So 2 theta equals to 60 degrees, we divided the equation by 2 and finally found out that theta equals to 30 degrees in its size. So this is angle theta that equals to 30 degrees in its size. Then I copied the yellow right triangle OBD in a new page and we analyze this yellow right triangle OBD. This is the right triangle OBD that I copied from the original drawing. This is angle theta that is equals to 30 degrees in its size. And side OD equals to R, that is the radius of our circle. R is the radius that we are looking for. In this right angle OBD times 30 degrees equals to OD over OB. Or times 30 degrees equals to DO over BO. Repeat again. In the right angle OBD times 30 degrees equals to OD over BD. OD is R. So it is R over BD. Times 30 degrees equals to R over BD. Here we multiplied this equation by BD and found out that BD times 30 degrees equals to R. Here we divided this equation by times 30 degrees and finally found out that BD equals to R over times 30 degrees. Here, this line segment BD equals to R over times 30 degrees in its length. Likewise, we actually did the same process on those two right triangles. We tried on the same process on these right triangles, the pink triangle and the orange triangle. Those two right triangles can go into each other according to side rule. I repeat again quickly. We have OF equals to OD, they are both the radii of the circle, therefore they are equal to each other. CF equals to CD according to rule number 2. Here CF equals to CD according to rule number 2. And finally, side CO is a common side that belongs to both triangles, so CO equals to itself. It's a common side. So we actually proved that all the three sides of the pink triangle OFC are corresponding equal to all the three sides of the orange right triangle ODC. Therefore, those two right triangles can go into each other according to side rule. And from the fact that those two right triangles can go into each other, we will derive that those two angles are also equal to each other. According to the rule that corresponding angles in congruent triangles are equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha because they are equal to each other. So alpha plus alpha equals to 75 degrees according to what is given as the equation. That is to say, 2 alpha equals to 75 degrees. 2 alpha equals to 75 degrees. Here 2 alpha equals to 75 degrees. We divide this equation by 2 and finally found out that alpha equals to 37.5 degrees. So actually, this is angle alpha, this equals to 37.5 degrees in its size. Then I copy the orange right triangle ODC in the new page and we analyze this orange right triangle ODC. This is the orange right triangle ODC that I copied from the original drawing. This is angle alpha that is equal to 37.5 degrees in its size, and side OD is the radius of this circle that is equal to R. In the right triangle ODC, times 37.5 degrees equals to OD over DC. Again, times 37.5 degrees equals to OD over DC. OD is R, so it is R over DC. Times 37.5 degrees equals to R over DC. Here we multiply this equation by DC. And finally found out that R equals to DC times 37.5 degrees. Here we divided this equation by times 37.5 degrees and finally found out that DC equals to R over times 37.5 degrees. Here, this side DC is equals to R over times 37.5 degrees. Then from the drawing, it is very easy to see that BC equals to BD plus DC. Again, BC equals to BD plus DC. Repeat again. BC equals to BD plus DC. BC equals to 2 units according to what is given as the equation. So we substitute BC by 2. BD equals to R over times 30 degrees. We substitute BD by R over times 30 degrees plus DC. DC equals to R over times 37.5 degrees. Therefore, we substitute DC by R over times 37.5 degrees. So in total, we found out that 2 equals to R over times 30 degrees plus R over times 37.5 degrees. Here we took R a second factor out of those two expressions and finally found out that 2 equals to R and R is taken as a common factor. So here, what is left from this expression after we took from it R as a common factor? What is left is actually 1 over times 30 degrees. And what is left from this expression after we took from it R as a common factor? What is left is actually 1 over times 37.5 degrees. So in conclusion, found out that 2 equals to R times 1 over times 30 degrees plus 1 over times 37.5 degrees. And so 2 equals to R and 1 over times 30 degrees is 1.732 plus 1 over times 37.5 degrees is 1.3032. So in total 2 equals to R times 1.732 plus 1.3032. 1.732 plus 1.3032 is 3.032. So in conclusion, found out that 2 equals to R times 3.0352. Here we divided this equation by 3.0352. Here 2 equals to R times 3.0352. We divided this equation by 3.0352 and finally found out that R, the radius that we are looking for, R equals to 2 over 3.0352. That is actually 0.6589. So in conclusion, in both methods, we found out that the radius R of this circle equals to 0.6589 units. Okay, thank you very much.